Until now, on the matter and radiation, I have uploaded a video in radioactivity and C14 carbon dating. Okay, C14 dating, and these two sections are much related. Today we will be looking at nuclear reactions. Okay, nuclear reactions. So it is much related to the nucleus. The previous ideas, the radioactivity or C14 dating, carbon 14 dating won't affect this. Okay, there is no relationship between them. So this is a separate section. Those who have not yet completed watching these two videos, make sure you complete them as quickly as possible. Okay. So let's look at the topic for today. So these are the basics. We already know this. When we consider the nucleus, the nuclei, it contains protons and neutrons. And collectively, we call them as nucleons. We have studied this in our chemistry. And then, these are some general information. The electron, proton, and neutron, their masses is given in kilograms. So if you look, the proton has slightly lesser mass than the neutron. And then let's look at the charge. Charge, this is the charge of an electron, and the charge of a proton is exactly the same but positive. And the neutron, it's neutral. Therefore, the charge is 0. Okay. Are we going to note along with this, or can you note it after the class? I'll just explain this. How shall we do? Next, the nucleus. What the nucleus is made up of? The nucleus is made up of protons and neutrons, right? They are made up of protons and neutrons. So let's say we have some atom. Its atomic number is 3, its mass number is 6, let's say. That means it's going to have 3 protons and 3 neutrons in its nucleus. Okay, it's going to have 3 protons and 3 neutrons. Before that, the nucleus, it's positively charged, and the electron goes around this nucleus, right? Why does this electron is attracted towards the nucleus? What's the reason? Electron is negatively charged and proton is positively charged. So there is an electrostatic attraction. Okay, there is an electrostatic attraction. But then, how about the nucleus? The nucleus, it contains protons and neutrons. The neutrons, they are already neutral. What we are left is protons, which has charges. And all those protons are positively charged. So, what can you tell about the electrostatic forces? Are they going to hold each other close together, or are they going to repel from each other? What has to happen? It has to get repelled, right? It has to get repelled. What is the reason? Because they are positively charged. But still, it is being held together as a nucleus. So, there should be some other strong forces that hold these protons together. And the neutrons also. The neutrons also. Do you agree with that point? There should be some force that is stronger than the electrostatic force. So that type of force, we call it as the nuclear force. Okay, we call it as the nuclear force. Nuclear force is much stronger than electrostatic force. But this nuclear force, they only act for a very short distance, very small separation. And electrostatic force, it can be seen even for somewhat larger distance. Okay, so the idea that we have some other nuclear force to hold these protons and neutrons together. Did you all get that idea clear? There has to be some other additional force. So nucleus are held together by strong interaction called nuclear force. Okay. And we know this representation, how to represent an atom. Let's say an atom X. It has an atomic number Z. So Z is written as subscript, and the atomic mass, it is written as superscript. When we have the same Z but different A, we call them as isotopes of the same element. So you already know that. Then we have the unified atomic mass unit U. So what is this U? You might have studied about AMU, right? In your chemistry, it's the same thing over here. So 1 AMU is identical, or is 1/12 of a C12 atom in mass. So that definition you already know. So 1 mole, we know that 1 mole of carbon is 12 grams, right? So in 1 mole, we are going to have Avogadro number. We are going to have Avogadro number of atoms. We are going to have Avogadro number of carbon, and that is equal to 12 gram. And then 1 carbon is going to be equal to 12 divided by that amount of atoms. So that is the mass of one single carbon atom. And the definition is we have to get 1/12 of 1 carbon. So we are multiplying by 1/12 the mass of a single carbon. Okay. So this is the mass of a single carbon multiplied by 1/12. So when we simplify, we get around 1.661 into 10 to the negative 27 kilograms. So 1 AMU is identical to this amount in kilograms. Okay. So you don't need to memorize these values, but you must get the idea. What is a AMU? What is 1 AMU? Okay. So from there, up to what we discussed now, all of them were the basics and you already know them. And now we are going to start something new that you uh, were not aware of before. So that's mass energy equivalence by Einstein. According to Einstein, he says that mass is equivalent to a certain amount of energy. And the relationship between that energy is given by the famous equation E is equal to mc squared. So his statement, according to special theory of relativity, a mass m is equivalent to an amount of energy E. So his idea is that mass is equivalent to a certain amount of energy. So that equation is E is equal to mc squared. So let's try to find out what is the energy of 1 AMU. How much 1 AMU is identical to in terms of energy. So we have the equation E is equal to mc squared. So what is the mass of 1 AMU? We already calculated it, right? 1.61 into this amount of kilogram. So we replaced kilogram and then the speed of light. So this term, this term will give us the energy in joules. Okay, this term will give us the energy in joules. But when we are dealing with the nucleus or when we are dealing with the atom, it will be very, very easy for us if we deal it in electron volt. Can you remember electron volt is also a unit for energy, right? It is also a unit of energy. So what is this AMU? Sorry, what is this electron volt? From electrostatic field, if you can remember, work done is equal QV. Now, what we are going to do is we are going to move an electron, through a potential difference of 1 volt. So, Q is the charge of an electron and V, that's 1 volt. So we get the work done is equal 1.602 into 10 to the negative 19 joule. So this is 1 electron volt. Remember? Can I tell that this amount of energy is equal to 1 electron volt. So if I divide this amount of energy, then I will get the amount of energy in electron volt. So when I calculate, it is around 931.5 mega electron volt. Are you clear with this idea? So what we have done is, we have found that 1 AMU is similar to 1 AMU is similar to 931.5 mega electron volt. Okay, up to this clear. Those who got the idea. Saja, how about you? Okay. So you don't need to remember how these values we apply and how we simplify it. Just remember the amount, okay? Because this is not exactly going to be equal to 931.5. Since we have rounded off the speed of light, we have rounded off the 1 AMU, everything we have rounded it off. Therefore, if you check the internet, this might sometimes deviate slightly, okay? So the idea is how to calculate it, and if you check the resource book, they have given as 931.5. So 1 AMU is equivalent to this amount of energy. Using that idea, let's calculate what is the equivalent. Using that, we also can calculate how much of energy that electron has in everything. To do that, first let's convert the mass of electron into AMU. We already know the mass, and we know what is 1 AMU. We know 1 AMU was that 1 AMU is equal to 1.661 into 10 to the negative 9, 10 to the negative 27 kilogram, 10 to the negative 27 kilogram. Then the mass of electron, we know it's 9.107, 9.107 into 10 to the negative 27, no, 10 to the negative 31 kilogram. So if we divide this amount, if we divide ME by 1 AMU, then we will get the mass of electron in terms of AMU. And if we calculate, it is around 0.00055 AMU. And if we do the same for mass of proton, we get this amount. And if we do the same for the neutron, we get this amount of AMU. Okay. So these are just not, so you don't need to remember the actual value to calculate. If they ask you to calculate, they will give all the information necessary. Okay. So now let's move on to the most important idea that we are going to discuss based on this, based on Einstein's mass equivalence. Okay, based on Einstein's mass equivalence. So a simple question: helium. What helium's nucleus consists of? Helium's nucleus consists of 2 protons and 2 neutrons. Okay, so if I combine 2 protons and 2 neutrons, I must get helium's nucleus. Agree with that? So do we have anything in addition to them? No, right? We only have 2 proton, 2 neutron, and it gives us the, it has to give us the helium nucleus. So what is the AMU of proton? That is 1.0073. Okay, 0073. How many protons do we have? We have 2 protons. And how many neutrons do we have? We have 2, and that is in AMU 1.0087. And the mass of helium atom, helium nucleus in terms of AMU, that's 4.0026. Okay, so AMU is also, we are measuring the mass, right? We are measuring mass in terms of a new unit. Do you have that idea? Now, in general, you make an object with A and B, and that combined object is C. If the mass of this is M1 and mass of B is M2, you would expect for the mass of C to be M1 plus M2, right? So here also we expect the same, isn't it? But let's look what's happening. So protons, if we find this value, we have to multiply by 2, 6, 14, 0, 2, plus multiply this by 2, 14, 1, 16, 17, 0, 2. Okay, if I add these two together, I get 0, 1, 12, 1, 3, 0, 4. So I get 4.0320. 4.0320 AMU. And here we have 4.0026 AMU. Are they equal? They are not equal, right? There is a reduction in mass. So let's find out how much mass has reduced. We call it as the mass defect. So this is equal to 4.0320 minus 4.0026. So if we deduct, we get around 8 correct. Okay, so this amount of mass is missing. This amount of mass is missing. But we know that 1 AMU is identical to, or the equivalent energy is 931.5 mega electron volt. So this amount of AMU, what is that equivalent to? So we have to just multiply that amount with 931.5. So that is 27. So this is, in terms of electron volt energy, 27.38 mega electron volt. So the missing energy, the missing mass, the mass defect has actually converted into energy. It has been converted into energy between the bonds. I mean, between to hold these protons and neutrons together, we have binding forces, right? So it has been converted for that. That is why there is a defect or reduction in mass. So this is the value we got in the resource book. The value was given as 28.3. So there was a lot of rounding off, right? That rounding off might have be the reason for this deviation. Okay. So this is the value we got, and this is the given value. Did you all get the idea? Did you all get the idea here? The idea is, if two things combine to form another uh, object or something, whatever, we expect the sum of the masses to be equal to the mass of that combined object. But in case of these nucleus, it is not as we expected. There is a difference in mass. So what we do is we find out how much of mass is missing, and then we when we check this amount of mass is missing, and the idea is this amount of mass has been converted as bond energy between those nucleons. Okay, so when we calculate, we got this amount of energy. Is it clear? Got the idea, or should I repeat? Taiba, how about you? Any doubts? Yeah, so binding energy, so that is a form of energy, right, Taiba? That is a form of energy, and nuclear force is a form of force. So if the binding energy, so how about this energy? Is this energy absorbed or released? This amount of energy is released, okay? During this reaction, the amount of energy we calculated, it is released. So it has become stable. If the amount of binding energy released is high, then force is high. Okay, then the nuclear force is high. I'll explain it next. Taiba, did you get a rough idea? Did I clear your doubt? And here we have considered helium, right? We have considered helium. In helium, how many nucleons do we have? In helium, we have 4 nucleons. Okay. Now, what we do is we divide this energy, this binding energy, by 4. So we call this one as the binding energy. This is the binding energy. So this binding energy is divided by the atomic mass. So atomic mass will be the number of nucleons. So we get roughly around 7.1 mega electron volt. So we get 7.1 mega electron volt. When we compare, so we know that helium is a very small nucleus, and in the periodic table, when I move along the group, along the period, or down the group, we know that the size of the atom is going to increase. Then the size of the nucleus will be increasing. Therefore, we will have a lot of protons and neutrons making bonds, right? During that, a lot of amount of energy is released. So the binding energy released will keep on increasing when we go along the group, along the period, or down the group. So it is hard to get a relationship among them. So what we do is we divide them by the number of nucleons they have. When we do so, now helium has 4 nucleons. When we consider carbon, carbon has 12 nucleons, and nitrogen has 14 nucleons, and so on. When we divide, what do we get? We get the binding energy per nucleon. So it's just like getting the average, right? how much of average energy does this release. So when we do that, this value, which was not having a certain pattern, falls into a certain pattern where it's between uh, 0 and 10. Okay, 0 and 10 mega electron volt. So it increases for some time and then remains constant and reduces. So here we draw a graph between atomic number or the atomic mass with binding energy per nucleon. Okay, are you clear why we avoided drawing graph between binding energy versus atomic mass and instead stick to binding energy per nucleon versus atomic mass? So is that point clear? Why we didn't choose this but chose this? Because this falls within a small range, okay, which we can compare. So in this graph, when we check the binding energy per nucleon with atomic mass, we get a variation like this. Okay, we get a variation like this. So in this graph, which part is stable? If we are at the bottom or if we are at the top, which one is stable? Think a bit. This is stable, 1, or bottom is stable, 2. Which one is stable? 1 or 2? Just tell your ideas. So generally, when energy is high, what can you tell about the stability? Stability is high or low? When energy is high, stability is low. Okay. When energy released is high, what can you tell about the stability? High or low? It's high. Okay. So binding energy, when I say binding energy, am I talking about the energy present in it or the energy released during that reaction? What are we talking about? Energy present or energy released? It is